So we're just going to discuss a few different types of tables and graphs and the type of data that they can display. And then we'll create a few. So let's talk about frequency tables first. A basic frequency table is going to have two columns. The first column lists all the categories of data, and the second column lists the frequency of each category. Which is the number of data values that fall into that category. Here's an example of a frequency table. And this is number of siblings maybe a class has. And so my categories are 0 through 5. And then I would ask each of you, how many of you have 0 siblings? And then you would raise your hand if you had 0 siblings, and I would count how many hands were up. Oh, there was only 1. How many have 1 siblings? And everybody who has 1 sibling raises their hand, and so on. Any questions about how a frequency table works? I'm going to have us make our own class frequency table. All right, here's the data I like to do. I think you can know a lot about a person and their favorite Sesame Street character. So that's going to be our data. So that's our first column, and then we'll do frequency in the second column. So who do we got? Name some Sesame Street characters. I know there's like a trillion. We're not going to do all of them. But some mainliners. We got your Big Bird. Your Snuffy. Grover. Who's the what? Oh, Abby Cadabby? Now, Bert and Ernie, yeah, do we do them separately or do we take them as one? B and E, Oscar, Elmo. No, that's a Muppet. That's not a Sesame Street character. Who? Oh, the Count, the Count. Cookie Monster. Are we leaving any important ones out here? I have Oscar. No, that's Winnie the Pooh.
Sorry.
Winnie the Pooh is the most boring British children's.
I love Winnie the Pooh.
It's so boring.
It is a book, but I love it.
Both of them. I feel like we are leaving somebody out. Nope. Also Winnie the Pooh.
Sorry. No, there's the pig is in
That's Muppets.
Sorry.
Although Kermit has crossed over. He's been in both. Kermit, yeah, he has been in there. I'll put him in. But I think do you guys know that Snuffleupagus, his storyline used to be that he was invisible and only Big Bird could see him?
Yes. I remember that.
And they made him be visible to everybody else because they thought it was like teaching kids to keep secrets from their parents when they went through trauma.
There was like a really old episode.
Oh yeah.
Where he loses his house and it was really sad.
And also, this is my theory alone, but because I have young kids, they were watching a lot of Sesame Street, and Snuffy is the only one who calls Big Bird Bird. He just calls him Bird, and I think it's because he's not big to Snuffleupagus. Yeah. All right. Here we go. So everybody needs to vote. You only get one vote. We're creating a frequency table. Favorite character. This goes for you too online, so just give me the hand up emoji when I get to your favorite character so I can count you in our frequency table. All right, Big Birds. Any takers for Big Bird? Bunch of Big Bird haters. 0. Snuffy? No Snuffleupagus. 0. Grover, that's me. Grover's great. Super Grover's great. All right, so just that book rules.
That is like the best book.
Abby Cadabby. All right, Shayna. Online, you have to vote. Bert and Ernie. 1, 2, 3, 4, 5. Bert and Ernie's good. You know what's really good were the claymation shorts. Bert and Ernie's Great Adventure. Have you seen those? What did I say? 5? Okay. Oscar? 1. Are there? Oh, 1, 2. Wait, no. I didn't put those down. I put them in there. Hold on, I gotta lower the hands. Let me try that again. Oscar? Naomi, 1, 2. All right, we got 2 for Oscar. Elmo? Prescott, that's for Elmo? Only 1. The Count? 1. The Count's good. Cookie? Cookie Monster. Ryan, 1. Oh, 2, 3, 4. Fan favorite. And Kermit, who I canonically think is more of a Muppet. Aiden, you're going with Kermit? You're a psychopath. Kermit is a Muppet. Okay. I don't know. Because Megan said that in the Wikipedia article it puts Kermit as a Sesame Street character.
We're not supposed to use it.
Actually very like
All right. So relative frequency, oftentimes it makes sense to look at relative frequency. It's just the proportion in each category rather than the raw count. So if I wanted to create a relative frequency table here, first of all, the total amount of data in my table is 2, 9, 10, 17. And so for each category, I would go through and divide the count by the total. So all the 0 ones are still going to be 0, but 2 divided by 17 is going to give me what? 0.118. So a little over 11% of people like Grover best. 1 out of 17.059. So about 6% like Grover. Bert and Ernie, the clear winners. 5 out of 17 is 0.294. Two out of 17 again is going to be 0.118. 1 is still going to be 0.059. 4 out of 17 0.235. And then this is 0.059. So when you total up the relative frequencies, they should add up to 1. So that makes 100% of your data table. All right. The cumulative frequency of any category is the number of data values in that category and all preceding categories as well. It only really makes sense to have a cumulative frequency if there is a natural order to your categories. There's not really a natural order to favorite Sesame Street characters. There would be no reason to have one in front of the other, so it doesn't really make sense to add up a cumulative relative frequency for this. But for this one, it would make sense because I could go, okay, how many people have 0 siblings? 1. And then I could say, how many people have at least 1 sibling? And what would the answer be? So 0 siblings is 1. How many people have at least 1 sibling in this table? At least 1. Oh, I'm sorry. At most 1. At most 1. I was saying it incorrectly. At most 1. And then I could go, how many have at most 2 siblings? 11. And so what we'd be is adding all the preceding categories up as we go. And so this one would be at most 3 siblings would be 15. At most 4 siblings would be 17. And at most 5 siblings is everybody in the data set. So because there is a natural order, it makes sense to come up with cumulative frequency in that context. All right. 2 types of data. Qualitative data describes qualities or categories. Quantitative data represents counts or measurements. Is our Sesame Street table qualitative or quantitative? Are Sesame Street characters qualitative or quantitative? Qualitative, right? Versus number of siblings is quantitative. You can have numerical data that is qualitative. So for example, zip code. While a zip code is a number, it's still a categorical variable, right? And the way to figure out if it's categorical or if it's quantitative, think about would it make sense to take an average? So while zip codes are numbers, does it make sense to take an average zip code? No, that would be a meaningless number, right? So when we deal with quantitative data, we'll generally put it into categories that we're going to call bins. And we can use those bins to graph it. All right, so let's just practice classifying a little bit here. Classify each of the following types of data as either qualitative or quantitative. Brand names of shoes in a consumer survey. Which one? Qual or quant? Yeah, qual. Just remember, quantitative is quantity. That's a number. Qualitative is a category. A synonym for qualitative is categorical. Heights of students. Quantitative. Audience ratings of a film on a scale of 1 to 5, where 5 means excellent. Yeah, that's quantitative. It makes sense to average those. That's how we get scores for movies on things like Rotten Tomatoes or Letterboxd. quantitative. No, that's not the right word. Quantitative. Too many T's. All right. So here's an example of binning. So I have 20 scores from a 100-point exam, and I've binned those scores in groups of 5 points. So 70 to 74, 75 to 79, 80 to 84, and so on. So these are called the bins. And then I've counted up the frequency. So how many people scored from 70 to 74? 4 people scored between 70 and 74. And then I've created a relative frequency category where I take the frequency and divide each one by 20. And that's going to give me my relative frequency. And then we can also look at cumulative frequency. So how many people got, right? At least a 95, only one person. How many people got at least a 90? Well, that's 3, because there's 2 that got 90 to 94 and 1 that got 95 to 99. So let's see. All right, we're going to talk about bar graphs and pie charts and then histograms. All right, I just wanted to make sure where we were at. Sorry. So a bar chart shows each category with a bar above whose length corresponds to its frequency or its relative frequency. So this is only, a bar chart is only for qualitative data. And you can make quantitative data qualitative by binning, like we did here. Right? And then pie charts are used primarily for relative frequencies, and the total pie must represent the total relative frequency of 100%. The size of each wedge is proportional to the relative frequency of the category it represents. So I'm not going to make you construct a pie chart because you would need to use a protractor, because that's how you figure out the angle of the size of the pie has to correspond to the relative frequency of that category. So for example, if I wanted to do grades here, if I wanted to categorize this quantitative data into grades, I could do this. That's an A, that's a B, that's a C, right? So basically everybody got one of 3 grades, an A or a B or a C. All right, so how many people got an A? 3. How many people got a B? 6. How many people got a C? 11. And then I could look at the relative frequency, so that's 3 out of 20. This is 15% got an A. That means 30% got a B. That means 65% got a C. All right, so if I wanted to create a pie chart, illustrating how many A's, B's, and C's there are, I would make each wedge, the angle correspond to the proportion that are in that category. So let's talk about how large would I need the wedge for the B category to be. If that's 30% of our student population got a B. How many degrees in a full circle? 360, right? So what proportion of 360 is 30%? We can just multiply 360 times 0.3. All right, that wedge should correspond to being 108 degrees. Does that make sense? This wedge should be 15% of 360. Well, that's going to be exactly half the 108. So that's going to be 54 degrees. 65%. 65% of 360 is 234 degrees. So you're not actually going to have to construct one, but I think there is one in like the open note quiz where they go blank percent fall in this category. What angle should the slice of pie for this pie chart should this category have? And that's how you figure it out. You multiply the decimal proportion by 360, and that'll tell you what angle that slice of pie should have. All right? Okay, so bar graphs are specifically for categorical data. There should be spaces between the bars. The bars should not be stacked against each other in a bar graph. All right, that's being put right next to each other as a special meaning, and that's in a histogram, which we're going to talk about in a moment. Things that you can lose points on very easily if you don't have. Make sure that your graph has a title, so you're telling your audience what it is that you're showing them. You need a vertical scale and title, horizontal scale and title, and then if there are multiple data sets being displayed, you should have some kind of a legend telling you how to read the graph. All right. So these are charts for quantitative data now. First one is called a histogram. It looks like a bar graph, but it's for quantitative data. The x-axis is a number line. And so in this case, the bars will be right next to each other unless there's like a gap in one of your bins. So if you don't have data in one of your bin set, then you may have just an empty bin and it'll look like there's a gap between the bars, but that has meaning. A line chart is basically the same thing as a histogram, except instead of bars, we just use a single point at the height of the frequency for each bin, and then we connect the dots. So I'll show you that here. So that exam score data, here's a histogram of exam scores. And then this line graph is the same thing, except all they did is they would put a single point at the height of each bar and then just connect the dots. You can see that gets me that line graph. All right. So I want to real quick show you how to use your calculator to make a histogram. So I'm going to get my calculator out, get a calculator out for yourself and follow along, because I'm going to do one and then I'm going to have you guys try one on your own. But let's use this, these 20 scores as an example. All right. Where's my calculator? Here we go. And again, you can use one of these on my desk if you need it. Here's what we're going to do. We're going to edit that data into a list. So you're going to find that list by going stat and then hit edit. If there's already data in there, scroll to the very top to the list name and hit clear. And then I'm just going to put my data in. So we have 20 test scores. So we have 76, 80, 78, 76, 94, 75. Nope, 91. All right, and I can see that I did enter the right amount of data. You can see this is the 20th cell right here. So I did enter 20 pieces of data. All right, so what I want to do is go to second mode just to quit to the main screen. I'm going to go into stat plot, which is second y equals. I'm going to choose the first option. I'm going to turn it on and then go down to the type. And the type, I want to select the one that looks like a histogram. It'll ask for where your data list is. Mine's in list 1. We'll keep the frequency as 1. And I'm happy with magenta. All right, so now I can go zoom. I'm going to go to my zoom window, and I'm just going to tell it zoom stat. That's the 9th option. There we go. So what your calculator will do, though, is it's going to auto choose how wide to make the bins. So if I hit trace, it chose to make my bin from 72 to 77.2. So it's made my bins 5.2 points wide. That one's 77.2 to 82.4. That one's 82.4 to 87.6. Now you can adjust that. So let's say we wanted to make our bins 5 points wide, like they had here. If I go to window, that X scale, XSCL, that's your bin width. So I can change it to 5. And then your X min is going to be the starting point of your first bin. So let's say I want it to be 70 because I want it to go like 70, 75, 80, 85, and so on. And I'll make my last one 100. And then I hit graph. There we go. Now it looks exactly like the one from the slides. If you hit trace, you can see my bin goes from 70 to 75. How many individuals scored between 70 and 75? Can you guys read that? So there are 4, right? And then if you scroll over to the next one using your cursor, this is how many people scored between 75 and 80? 7. Questions on that? Okay. Let me share. All right. So let's do this one. I want everybody to attempt it. Try and make a histogram using your calculator. Oh, you know what? You don't have to use your calculator. So for this one, they've already binned it for us. So we can just sketch it by hand. And so this is the age and the number of actresses in those age groups that won an Academy Award. So these are binned in 10-year groups. So the way I would do this is go, okay, 20, 30, 40, 50, 60, uh-oh. All right, 70, 80, 90. So we would label this age. My y-axis is going to be my frequency. All right, so my biggest frequency, age 20 to 29, there are 30 actresses. I'm going to do 10, 20, 30. All right. So we have 30 in that age group. And I labeled this 20, 30, 40, 50. It's generally understood that the right endpoint is not included in that bin. And you saw that even on my calculator. So if I pull up the calculator, notice that the bin that it's on, it goes min equals 95, max is strictly less than 100. So 100 isn't included in that. Does that make sense? So it's understood that the right endpoint will not be included in that bin. All right, so 34 for the next age group. 13, big drop off. 1, 50 to 60. And then somehow another increase, 60 to 69 is 6. 70 to 80 is 1. What female has won an Academy Award that was 80 to 90, do you think? There's only one. Any guesses? I'll bet Dame Judi Dench. Maybe. All right. So that's the basics on how to hand sketch a histogram. And then a time plot is just a line graph, but where the x-axis is specifically time. So this is a time plot of the US homicide rate from the years 1960 to 2012. And that's homicides per 100,000 people. These are pretty intuitive to read. So you can see the peaks. Homicide rates had significant increases in like the late 70s, early 80s. I don't know what that was about. But in your lifetimes, it significantly decreased. And that's it. Got a problem set, so you got about 35 minutes.